An Eulerian trail, also called an Eulerian walk, is a walk in a graph that uses every edge exactly once. If the trail starts and ends at the same vertex, it is called an Eulerian circuit or Eulerian cycle. For a graph G equals V, E, a trail T is a sequence V0, E1, V1, ... EK, VK, where each EI is an edge, the set containing VI-1 and VI, and each edge of E appears exactly once in T. A trail cannot repeat an edge, but vertices may be revisited. An Eulerian circuit is a closed trail. A graph that contains one is called Eulerian. An Eulerian trail that is not closed exists in a graph called semi-Eulerian. Imagine a postman who must deliver mail on every street exactly once and then return to the post office. That route is an Eulerian circuit if the post office is the starting-ending point. Euler's theorem, 1842, gives a simple degree test for the existence of an Eulerian circuit or trail in a connected undirected graph. Statement: let G be a finite connected undirected graph. G has an Eulerian circuit if and only if every vertex has even degree. Degree of V is even for all V in V. G has an Eulerian trail but not a circuit if and only if exactly two vertices have odd degree. The trail starts at one of the odd degree vertices and ends at the other. Proof sketch both directions. Necessary: assume C is an Eulerian circuit. Traversing C, each time we enter a vertex we must also leave it, contributing 2 to its degree. Hence, every vertex is incident to an even number of edges. If T is an Eulerian trail with distinct start S and end T, all interior vertices are entered and left the same number of times, so they have even degree. Only S and T have an extra incident edge, giving them odd degree. Sufficient: suppose all vertices have even degree. Pick any vertex V and start walking, always choosing an unused edge. Because the degree is even, we cannot get stuck at a vertex before returning to V unless all incident edges are used. The walk therefore returns to V, forming a closed trail. If there are still unused edges, they must be incident to some vertex on the current closed trail, otherwise the graph would be disconnected. Splice a new closed trail starting at that vertex into the existing one. Repeating this splicing process eventually uses every edge, yielding an Eulerian circuit. The case of exactly two odd vertices is handled by adding a temporary edge between them, applying the even degree case, then deleting the temporary edge, leaving an Eulerian trail. Explanation: 2 classic constructive methods are Fleury's algorithm, simple but slower, and Heyerhaeuser's algorithm, efficient, O of E. Example graph: the classic Königsberg bridge layout modeled as a multigraph with vertices A, B, C, D, land masses, and edges representing the 7 bridges. Fleury's algorithm steps: Step 1: start at any vertex with odd degree. Here all 4 vertices have odd degree, so pick A. Step 2: at each step, choose an edge that is not a bridge of the remaining graph unless there is no alternative. Bullet point: from a you can go to B via edge E1. Removing E1 does not disconnect the graph, so it is safe. Bullet point: continue similarly, always checking whether removing the candidate edge would increase the number of connected components. Step 3: after 7 selections, you obtain a trail that uses every bridge exactly once. Because the Königsberg graph has 4 odd-degree vertices, Fleury's algorithm will finish with an Eulerian trail, not a circuit. Heyerhaeuser's algorithm steps: more efficient: Step 1: choose any vertex with non-zero degree, say A, and follow edges arbitrarily until you return to A, forming a closed cycle C1. Step 2: if some edges are still unused, pick a vertex V on C1 that has unused incident edges and start a new cycle C2 from V, returning to V. Step 3: splice C2 into C1 at V. The combined walk now covers edges of both cycles. Step 4: repeat until no unused edges remain. The final walk is an Eulerian circuit or trail if you started at an odd vertex. Applying it to the Königsberg graph yields the same trail as Fleury's method, but with far fewer bridge checking operations. A Hamiltonian path is a simple path that visits every vertex of a graph exactly once. If the path's start and end vertices are adjacent, the path can be closed to form a Hamiltonian cycle or Hamiltonian circuit. Notation: for a graph G equals V, E, a Hamiltonian path is a sequence V sub 1, V sub 2, up to v sub v such that v sub I and v sub I plus 1 are in E for each I and all vertices appear exactly once. A Hamiltonian cycle adds the edge v sub v and v sub 1. Vertices are not repeated. Edges may be used at most once because a simple path cannot have repeated vertices. Unlike Eulerian problems, the condition is about covering vertices, not edges, making the problem generally harder and NP-complete. Terminology: a graph that contains a Hamiltonian cycle is called Hamiltonian. A graph that contains a Hamiltonian path but no cycle is sometimes called traceable. Real-world analogy: think of a traveling salesman who must visit each city exactly once and return to the starting city. That route is a Hamiltonian cycle, ignoring distances. Two classic sufficient conditions guarantee Hamiltonicity in a simple undirected graph with n greater than or equal to 3 vertices. Dirac's theorem, 1952. If every vertex has degree at least n over 2, that is, degree of v is greater than or equal to the ceiling of n over 2 for all v and v, then G is Hamiltonian. Example: the complete graph K sub n has degree n-1, which is greater than or equal to n over 2 for n greater than or equal to 3. Therefore, it is Hamiltonian. A less trivial example is the cycle plus chords graph on 6 vertices where each vertex is connected to its 2 neighbors on the cycle and also to the opposite vertex. Every vertex has degree 3 equal to 6 over 2, satisfying Dirac's condition, and indeed a Hamiltonian cycle exists. Orr's theorem, 1960. If for every pair of non-adjacent vertices u and v we have degree of u plus degree of v is greater than or equal to n, then G is Hamiltonian. Example: take a 7-vertex graph formed by a 7 cycle, each vertex degree 2, and then add edges from vertex 1 to vertices 4, 5, 6, increasing its degree to 5. For any non-adjacent pair, the sum of degrees is at least 2 plus 5 equals 7, satisfying Orr's condition, and the graph indeed contains a Hamiltonian cycle. Both theorems are sufficient only. Many Hamiltonian graphs do not meet the degree thresholds. Explanation: while there is no simple necessary and sufficient condition for Hamiltonicity, the problem is NP-complete. Several necessary criteria can rule out a Hamiltonian cycle. 1. Degree sequence test Bondi Ch-Vattel. If a graph's degree sequence d sub 1 less than or equal to d sub 2 less than or equal to d sub n fails the inequality d sub I greater than or equal to I or d sub n minus I greater than or equal to n minus I for some I, the graph cannot be Hamiltonian. Counterexample: consider the bow tie graph consisting of 2 triangles sharing a single vertex. Its degree sequence is 1, 2, 2, 2, 2, 3. The vertex of degree 1 violates the necessary condition, and indeed the graph has no Hamiltonian cycle. 2. Ch-Vattel-Erdos condition, 1972. Let cap of G be the vertex connectivity, the minimum number of vertices whose removal disconnects the graph, and alpha of G be the size of the largest independent set. If cap of G is greater than or equal to alpha of G, then G is Hamiltonian. Illustration: in a complete bipartite graph K33, kappa equals 3, removing any 2 vertices leaves the graph connected, and alpha equals 3, each part is an independent set of size 3. Equality holds, and indeed K33 is Hamiltonian, a 6th cycle exists. Conversely, if kappa is less than alpha, the graph may still be Hamiltonian, but the condition tells us nothing. These criteria provide quick ways to disprove Hamiltonicity without exhaustive search. Explanation: comparing the two concepts reveals that they measure different things: edge coverage versus vertex coverage. Eulerian but not Hamiltonian: the classic house graph. A square with a triangle roof has vertices of degrees 2, 3, 2, 3, 2. It has exactly 2 vertices of odd degree, so it possesses an Eulerian trail. But there is no cycle that visits every vertex exactly once because the roof vertex of degree 3 forces a repeat. Hence it is semi-Eulerian but not Hamiltonian. Hamiltonian but not Eulerian: the 5-vertex cycle C5 is Hamiltonian. The cycle itself visits all vertices. However, each vertex has degree 2, even so the graph is Eulerian actually. Need a better example. Consider the star graph K14, it is not Hamiltonian, cannot visit all leaves without returning to the center. For the reverse, take the Peterson graph. It is Hamiltonian, contains a 10 cycle, but not Eulerian because it has vertices of degree 3. Odd, giving 3 vertices of odd degree, violating Euler's condition. These examples show that satisfying one set of conditions does not imply the other. The two notions are largely independent. Problem 1, Eulerian check. Given the graph G with vertex set a B, C, D, E and edges a B, B, C, C, D, D, A, E, B, E, C, E, D, E, determine whether G is Eulerian, semi-Eulerian, or not Eulerian, and draw an Eulerian trail or circuit. Solution, compute degrees. Degree of A equals 2, degree of B equals 3, degree of C equals 3, degree of D equals 3, degree of E equals 4. Exactly 3 vertices B, C, D have odd degree, so the graph fails both Eulerian and semi-Eulerian conditions. Hence G is not Eulerian, no trail uses every edge exactly once. Problem 2, Hamiltonian cycle construction. Let H be a graph on 7 vertices where each vertex is joined to the next 2 vertices in a cyclic order, that is, edges Vi to Vi plus 1 and Vi to Vi plus 2 modulo 7. Prove that H is Hamiltonian and list a Hamiltonian cycle. Solution, for any 2 non-adjacent vertices Vi and Vj, the distance on the cycle is at least 3, so each has degree 4. Hence degree of Vi plus degree of Vj equals 8, which is greater than or equal to 7, the number of vertices. By Orr's theorem, H is Hamiltonian. A concrete Hamiltonian cycle is V1, V2, V4, V6, V3, V5, V7, V1. Problem 3, applying Dirac. A simple graph G has 10 vertices, each of degree at least 5. Show that G contains a Hamiltonian cycle. Solution, since the degree of each vertex is greater than or equal to 5, which equals 10 divided by 2, Dirac's condition holds. Therefore G is Hamiltonian. Problem 4, constructing an Eulerian circuit using Heyerhaeuser. Use Heyerhaeuser's algorithm on the Königsberg bridge graph, which has vertices A, B, C, D with 7 edges as in the classical example, to produce an Eulerian trail starting at A. Solution sketch. First, start at A and follow the edges A to B, B to C, C to A to D, D to C, C to B, B to D. All edges are used, and the resulting trail A to B to C to A to D to C to B to D is an Eulerian trail. Because there are 4 odd vertices, so no circuit exists. The step-by-step splicing in Heyerhaeuser collapses to a single walk because each new edge leads directly back to the current trail. These problems test the ability to apply degree criteria, construct required walks, and use algorithmic techniques.